Okay, welcome back to lecture 4 of Design of Machine Elements and Systems in Agricultural and Biosystems Engineering. This is still on the topic of velocity analysis, uh, coming from the topic of the graphical method of velocity analysis. Now, uh, in this lecture, the discussions will be on the instantaneous center of velocity, okay, instant centers, okay, instant centers, and then the centros, and then lastly, a topic on the velocity of slips. Okay, now proceed. Okay, uh, there's this definition for the instant center of velocity, and it is a point about which a body is rotating at a given instant, and to which, okay, the velocities of the particles or points in the body are relatable. Why? Because they are one body, okay? They form one link. So in one link, the various points or the particles of that link, okay, which is a body, would be revolving around a certain center of velocity, okay? The center of velocity would have a zero, okay, zero velocity, and that's why in a wheel, okay, the point of contact of the wheel to the surface is the instant center of velocity, or what is called instantaneous axis of velocity, or IAOV. Now, shown is a link AB, and to find the IAOV, okay, given the the velocities, okay, of certain points of that bar, okay, of that link. So you have point A moving in this direction, okay, and then point B is moving in this direction. Now to do or to find the IAOV, okay, so what should be done? So it's possible that this could be connected to a link that's causing this to move this way, right? So it's possible that the link would be moving, moving this way, so that this would force this link to move this way. To find the IAOV, or the instant center of velocity for this link, okay, this link AB, you project, okay, this should be actually 90 degrees. Apologies for the drawing. Should be corrected, but should be 90 degrees, okay, and this one should be 90 degrees, and the projecting that 90 degrees line, okay, would from both, okay, from both velocities would lead to a point that is now the AOV. Now, if you project, for example, this if, for example, the velocities of this are unknown, but if you know this velocity, okay, for example, this is 2 meters per second, then, okay, if this v of a is unknown, it could be projected along this line, okay, and could be known of the velocity, okay, based on this IOV. So it's perpendicular, okay. Now, the total number of instant centers of a mechanism can be determined by the formula. Okay, this is just the combination formula. So it's n times the quantity n minus 1, the quantity all over 2. Okay, so for example, for a 4-bar linkage, okay, you would have 4-bar linkage would have n centers, okay, 4 times 4 minus 1 all over 2 would give you 12 over 2, which is 6. So there are 6 instantaneous axes of velocity. To show, okay, the use of this IAOV, it would be best to solve for the previous problem. Okay, it was already solved using the graphical method. uh, this would have the same, okay, same solution, okay, given that it's the same problem. Okay, no, same answer. Okay, it's given it's the same problem, but different solution. Okay, using the IOV. Okay, so let's try to do this. I'll share different. Okay, so I hope the student is already familiar with the drawing, and let's go back to our CAD, okay, our computer-aided design software, so that we can do um, the solution. So we have a 220 centimeter, okay, velocity going here. So what we do is it's perpendicular to that, right? So that actually that length is 20 centimeters in length. No, no, um, it represents a 20 centimeters. It's not, but anyway, it's actually 20 centimeters. But what we do is we do the uh, it's not, we do the same, okay, the same uh, line, okay, to represent the 20 centimeter per second velocity. Okay, rotate, rotate. Okay, right. So we rotate it 90 degrees. Oh, sorry, it should be negative 90. And well, that represents the okay, that represents the velocity. And what we have to do now is to, right, we're trying to find what? We're trying to find the velocity of V, okay, VC, okay. So we have our link, our slider here. So it's moving this way, and we want to find that. So we are interested with this link, okay, this link BC, and we're trying to find VC, okay. So we have already this value, right? Now we're trying to find we want to find the um, instantaneous center of velocity of this um, this link, okay. So we know that the velocity of VC is along this direction because it's in sliding contact, okay. It's a translational motion, okay. So what we do is we make a line that projects here, okay. This line, okay, vertical one. Take out of the colors because I'm trying to. Anyway, it should be different for uh, every type of line. Okay. We make now a line that's perpendicular to that this line. Okay. So it's another X line. We are going to do something from here to here. Okay. So it will so let's just show all of the drawing so that you can appreciate the full of it. So this is now the IOV of that uh, of link, okay, of this link BC, okay, BC. So what we do is we now, okay, we translate this value, okay, over here. And what we can do is what? We create a circle from this point, the IOV, and we make one up to the location of this uh, location of our C. Okay, so we can say that we have the center at this IAOV. Okay, and we have to do now. What we have to do now is create a line. Okay, it's passing through that IAOV, and okay, let's first correct our colors for lines so that there's no confusion. Okay, so those are construction lines that will show the, well, those are just accessory lines that would help us find the actual values for our nodes. So we put now a construction line, an X line again, okay, along what our our known velocity, okay, our velocity of known magnitude, and that it pass through the IAOV. Okay, and then we create now a line, okay, that is perpendicular to this line, okay, so that, okay, so we create a line that is perpendicular to this line. Okay, I'm going to rotate it 90 degrees. Uh, 90 degrees. Right, so we will now move that from this point, that point, so that we can get the actual value, okay, of this VC, okay, and that would now be what? Okay, let's try to again correct the colors of our lines. Okay, so our VC now is from here to here. Okay, let's change the color so that you can correctly identify it. All right, so that is now our VC, and we can get the magnitude of that simply by measuring it. Okay, so the value is what? It's 22.8, similar to what we found, okay, with the graphical method, and it would actually be consistent also with the values for the analytical method. All right, so this is a very simple method to use, okay, using just the geometrical properties of the velocity properties using the IAOV. Okay. Okay, so that's how to use the instantaneous axis of velocity. Okay, and we now move to the centro, which is just an enhancement of the IAOV actually, and that unfortunately the centro does not apply to this 3-bar linkage that we have at the moment. Okay, again, why wondering this is a 3-bar linkage when you are only seeing 2 links? Okay, you actually have 3 links, okay, from over here. Okay, so you have your link over here, link 1, this is link number 2, and this is link number 3. So the frame is considered a link. All right, so let's move to our centro, okay, and the centro is a point, okay, lying in 2 links having the same velocity vector in both the 2 links. When you say velocity vector, it's magnitude and direction, and the centro is based, okay, it's based on the Kennedy's theorem, and it's stated as, okay, you have 3 links having 3 centros lie on a line. Now it's a theorem because the theorem or the statement or that statement fails at some point, and it's for, okay, it's for bodies, okay, that are okay, or linkages that have no relative motion. Okay, so the central. How do we go about with the central? Okay, so the same formula for the determination of the centers, the instant centers, is the same for the centros. It's n. Okay, it's sorry, it's n. Okay, n equals centros. That now stands for centros, and times n minus 1 over 2. And you would have what for this one? You have link 4 links here. So 1, 1, 2, 3, 4. So you have still the same number of links for this kind of mechanism. Okay. Now, what happens to the central? So each 3 points in a 3 links would have one central, and so this one would have you have here you have here a 2 link. So you have 2 links. You have, for example, these 3 links, this one, and this one would have what? Would have a link 0, 1 over here. This is link 0, 1. This is link no, we have to state first that this is link 0. Link 0, link 1, this is link 2, and this is link 3. This is 0, 1. That is just the pin, but this is 0, 1. This is 1, 2, and this is 2, 3, and this is 3, 0. Or 0, 3, or 3, 0. Now there are 2 more. Since we have 6 centros, where are the others? So it's important to say that there are unknown centros in here, and it's because why we have a different combination still. So we have 6 centros. 0, 1, 1, 2, 2, 3. And then we have 3, 0, and we still have what? 0, 2, and then we still have 1, 3. These are the known, the known centros, and these 2 are unknown. And why unknown? Because they are located outside of the bodies. So they're located outside of the bodies of this this mechanism. So what we do is we find them. For example, in this linkage, so we have that centro, that is actually centro 0, 0, 2. This is 0, 2. So it's between this link and this link. Now the steps to find the centro is, used to solve for the known values of the magnitudes of your velocities. Because again, this is a velocity analysis method. So the steps of the centro method is to identify first the unknown centros. So we have 1, and then we locate the unknown centros. We identified 2, and we have already located 1. And then afterwards, we can use those centros to find for the known velocities using the same method we used for our IAOV. Now let's try to solve if, for example, there is a known value for the rotation, for example, of this. You have a known value for your rotation. So this is rotating at 200 rad per second. Okay, so what we do to find our centro is we have already located one, and it's 0, 2. Okay, and we have our links. Okay, link 0, link 1, link 2, link 3. Sorry. All right, so what we can do is we can actually proceed, finding we can go the graphical method route, or we can go the IIOV route in solving for the unknown values of a certain thing. Okay, so in this, for example, in this value, so we know from the fact that we have here 200 rad per second that there's a velocity 1, 2 here. So let me just use the annotate. Okay, so you have here velocity 1, 2, and you have here, since this is rotating here, and this would force this bar to go this way. Okay, we can actually just assume first the values for our rotation. So if, for example, we have an assumed direction here, if it's negative, the value that we find for our magnitude is negative, so we can just revert it, and then it would mean that it's in the opposite direction. Now, what we intend is to have our velocity 2, 3 here, because that is a known, and it's perpendicular to that link. What if we want, for example, to find the velocity of a certain point of this bar of this link 2, VP? Now, to solve that, since we can immediately form our graphical method or analytical methods, that V23 is what? V12. Applying the analytical method to solve for the central, because we have our central here, so we have V23, it's known, and what? It's actually it's directly proportional to the length, of our distance to the central. So it's 0, 2, 0, 2. Where's that 0, 2? Our 0, 2 is over here. So we have our 2, 3 here, we have our 1, 2 here, and our 0, 1 over here, and our 0, 3 over here. So our 0, 2 minus 2, 3, is over 0, 2 minus 1, 2. That would indicate the length, the length of the distance of that. So it's proportional to the distance, the same way we did our proportionate solution a while ago with the IOV. So we have our V23 equal to what? It's 2, 3. Actually, it's actually 2, 3 minus 0, 2, so that we're not confused. So we have our value for the velocity of the 2, 3. It's 1, 2 over 2 times what? The velocity 1, 2, because we can get whatever the length of the length of this link is. For example, the length of this is, for example, x. So 200 x is the or whatever the unit is. So unit per second, and then we have our value for V23, and we can get also the velocity of 2, it's going to be what? That's link number 2, right? So we have our V12 over what? 1, 2 over 0, 2, and that's going to rotate about what? This 0, 2. That's the value, whatever that value is. Now, to get VP, which is the unknown that we want, we simply get what? P minus 0, 2, that is a distance over here, B minus 0, 2, all over what? 12. Sorry, I wrote in the wrong. I wrote in the wrong location. All right, so v minus 0.2 over 12. Okay, no, 1, 2 minus 0.2, and you just multiply that by v12. Okay, this is again proportionate to the value. Okay, again, similar property that we did with our IAOV. So this, if you project that here, okay, it's going to have a value that's proportionate, and that's why, okay, we are using this proportionate equations. Okay, so that is the use of the centros. It's best to use this for 4-bar linkages, beginning with 4-bar with linkages that have 4 bars or links. So that's the use of our centro. Now we move over to our topic of our velocity of slips. Now the velocity of slips, okay, happens in rolling contacts, and rolling contacts are happening in round objects such as probably wheels, pulleys, cams, okay, and round objects, okay, roll when the coefficient of friction mu is greater than 0. Okay, so that's the condition for our slippage, or no, the rolling to happen. And we're going to talk about slippage, and this is going to be far more important in pulleys in the case of mechanisms and also cams. Okay, but okay, to proceed with the discussion, okay, so we have a, sorry, got the wrong pen. So you have a round, okay, a round object. So it could be a wheel. Okay, so a wheel is rotating what? It's going to rotate, okay, that way. So you have your, for example, a rotation of W, and okay, a general plane motion, okay, just as this one, would have what? A translational movement, okay, as well as, okay, so a v translational and a rotational. Okay, so you have your rotation while it moves. Okay, now sliding, okay, of course, when, okay, the v translational, I'll shorten it to trans, is greater than the v rotational, so I will shorten that to rot, and then rot. Okay, so what happens is, you have the translational over here, so at the center of the body, right? So at the point of contact, same is happening. Okay, the translational is over here, and you have your rotation at that point, for example, is, so that is a v rot, and the net, okay, the net of that is, okay, this one, for example, v net, and that is what? It's should be greater than the frictional force. Okay, sliding is, that's what's going to happen. Okay, no, I mean, there's still going to be frictional force in here. So sliding, okay, is also called forward slipping. Okay, another case, okay, is the, okay, slipping. Okay, okay, slipping. We go now to sleeping, not SLEEP. Okay, sleeping. It's slipping. Now, This of course now, okay, when your V trans is less than the V rot. How's that going to happen? Okay. Okay, so your rotational could be very big, okay, compared to your translational. Okay. So same W here. And okay, the rotational velocity. Okay. And then you have, for example, your translational velocity over here. So the net is going to be what? It's going to be V net, for example, is here. And you still have a frictional velocity, frictional coefficient, force from frictional force along the opposite of that. Okay, and this would be best shown, okay, using an example. Okay, how's that applied? Okay, right. So a rolling pulley has a velocity of 5 meters per second at its center of mass. And what's being asked is if this pulley is in pure rolling contact, okay, against the surface it's rolling on. Given that the angular velocity, okay, is 3 rad per second, okay, and the pulley diameter is 300 centimeters. Okay, so from here, okay, we know that the velocity of the center of mass, okay, at the center of mass of the object is VCM, which is equal to your translational, okay, and it's given, so it's 5 meters per second, and you have your V rotational, which is what? It's actually the V tangential of your pulley, okay. Given you have a pulley, okay, you have a tangential component, okay, normal and tangential component of your velocity, okay. When you are trying to solve your velocity, your angular velocity, okay, and it's going to be what? The radius, okay, times the angular velocity, and it's what? It's going to be, okay, so you have 0.15 meters, okay, from this one, and you multiply that to the rad per second of 3, okay, and you get what? There's going to be 0.45 meters per second, and since we have our V trans, okay, greater than our V rotational, so it means that a sliding rolling motion, not a pure one. So that's the very use of the velocity analysis in slippage. Okay. In the next topic, this will be progressing into the analysis of the acceleration of machine components. Thank you for listening.